In this episode of Vector Search Optimization Techniques, we will learn about query re-ranking. In query re-ranking, we take the initial results returned by the vector search and then reorder them to surface the most relevant items at the top, using specialized models that are called re-rankers. Re-ranking happens after retrieval. The first step retrieves a set of candidate documents that are broadly relevant but not perfectly ordered. Re-ranking then refines this list by evaluating deeper semantic relevance to the user's query. It can also incorporate metadata signals such as recency, which can be measured by the last update date on the chunk, or source authority, which can be measured by the source system information on the chunk's metadata. One practical implementation is to generate a short contextual summary of the chunk using a large language model at the time of ingestion. This summary can be saved in the metadata and then later be passed to the re-ranking model for making more accurate relevance judgments. There are three main types of re-ranking approaches. The first approach uses cross-encoder models, often considered the most accurate re-rankers. In this approach, the query and each document chunk are combined and passed together into the model, which outputs a relevance score. Because the model processes both inputs jointly, it captures deep token level interaction between the query and the document chunk. This leads to very high accuracy, but also high computational cost since every query and document chunk pair must be evaluated separately. For this reason, cross encoders are typically used when we are re ranking a relatively small set of results, usually up to around 100 documents. Cross encoders are available both as managed APIs and open source models, for example, via Hugging Face. You can self host these models to reduce latency in production systems. The second approach is to use late interaction models, which are Colbert style architectures. In the late interaction models, we use token level embeddings, which means we convert every word or token in the query and in the document chunks into its own vector embedding. Rather than working with a single vector for the entire query or the document chunk, every word or token gets its own vector representation. We pre-compute and store token-level embeddings for all documents ahead of time in a separate vector index. This avoids recomputing them during the re-ranking process. When the query arrives, we generate token-level embeddings for query on the fly and then use a special scoring method called max sim scoring to compare each query token vector with all document token vectors to measure similarity and produce a relevance score. We use the fine grained relevance scores to re rank the candidate documents. Because in this approach, we pre-compute the document token embeddings in advance and store them in a vector database, this approach scales much better than cross-encoders while still maintaining strong accuracy. Late interaction models are well suited for re-ranking larger candidate sets, typically in the range of 100 to 1000 documents, or when your use case requires very low latency. Because late interaction models generate token level embeddings, they need special support for multi-vector representations. Vector databases such as Milvus and Quadrant provide native capabilities for storing and querying multiple vectors per document. So if your use case requires late interaction re-ranking, you must consider the right kind of vector database. The third approach uses large language models for re-ranking. Instead of relying purely on similarity scores, large language models read, query, and document and reason about their relevance. This makes them the most flexible and powerful approach, especially for complex queries. However, it is also the most computationally expensive approach. As a result, large language model based re ranking is typically applied to a very small set of top candidates, often the top 5 to 10 results. In practice, these approaches can either be implemented on their own to improve vector search performance, or they can be combined in a cascaded ranking pipeline. The initial retrieval brings back candidates. Late interaction models refine the larger sets. Cross encoders perform deeper ranking. And large language models provide final high quality judgment. As a rule of thumb, 100 to 1000 candidates, you should use late interaction. 20 to 100 candidates, you should use cross encoders, and 5 to 10 candidates, you can consider LLM based re ranking. However, depending upon your use case's unique latency and accuracy requirements, you must evaluate these approaches either individually or together as a cascading ranking pipeline.